Good morning. Welcome everyone at the third day of the RF technology event. Today we have 5 interesting webinars on the program for you. We start today with a presentation of Mike Gathergood from Bird Technologies on behalf of Heynen. The title of his presentation is How to Use Handheld Test Equipment for Field Engineers Working on Critical Communication Systems, LMR, to Your Advantage. The presentation is around 45 minutes. We have room for questions, time for questions at the end of the presentation. So feel free also during the presentation of Mike to fill in your questions in the public chat. If you want to have the presentation on full screen, you click on the screen where you see me now, and you can get on full screen mode to get a complete view of the presentation. All right, let's switch on to Mike Gathergood from Bird Technologies. He's situated in the UK, close to London, he just told me. So I will say good luck with your presentation. For the audience, have a nice webinar.
Thank you, Mark. Good morning, everybody. Welcome to Bracknell in the south of England. As you can possibly see from the windows behind me, it's still dark here, and it's also cold and wet, although we have snow forecast for tomorrow at the moment. Okay, how do I start this presentation? I'm not sure how to change pages. Right, okay. Well, there's nothing particularly new about the concept of handheld test equipment for installers of land mobile radio systems. What I would like to show you this morning is how the technology of the millennial, in other words, tablet hardware and the Android operating system, allow us to make that test equipment more functional and easier to operate. I'm sorry, I'm not sure how to switch to the presentation here. Mark, can you possibly help me? Ah, thank you. Okay. So let's look first at a handheld antenna and cable tester, which uses the principle of frequency domain reflectometry. Again, there's nothing new about this technology. In fact, it's been around in its various forms for more than 20 years, but we can do a great deal to improve its user friendliness. If we apply a swept or a stepped frequency signal to any real-world antenna and transmission line, we will get a very complex reflected signal of various phase delays and amplitudes, representing the distance and return loss of every part of that system. We can use inverse fast Fourier transformation to interpret and display those reflections in a number of ways in order to provide the installer or service engineer with useful diagnostic information about that system. Displaying the sum of all the amplitudes on the y-axis and the range of frequencies on the x-axis show us either return loss versus frequency or VSWR versus frequency. Displaying the amplitude on the y-axis and the time delay on the x-axis could show us the distance to any faults that may be present on the system. If we disconnect the antenna and leave the cable open circuit, we can derive the loss of the coaxial cable at any given frequency, allowing us to cross-reference that cable manufacturer's specifications and verify whether the cable is good or bad. Coaxial cable is prone to absorb moisture if any connections are not properly sealed, and this will, in time, increase the cable losses. I'm not sure how to change slides again. If you could help me, please, Mark.
Yeah, Mike, it's really easy. If you use the right arrow on your laptop or computer, you will get to the next screen, next slide.
Ah, right, thank you.
Yeah, good luck.
It's easy when you know how. Okay. So here's an example of a return loss versus frequency display might look on our Android instrument. Return loss is a measure of the ratio of the forward power to the reflected power. Ideally, we want all of the power leaving our transmitter to be radiated by the antenna system. But the reality is that our antenna isn't perfect across the entire range of frequencies, and some of the power will be reflected. For example, if our transmitter produces 100 watts and the power reflected back to the transmitter is 1 watt, the return loss is 20 dB or decibels, since 100 watts is 20 decibels larger than 1 watt. The higher the return loss, the better the system. In our example, the y-axis shows the return loss in decibels and the x-axis shows the frequency in megahertz. Our color screen allows us to display the information in a user-friendly manner. The touchscreen allows us to rapidly change any parameter as we desire. The Android operating system allows us to make a screenshot and to export the resulting JPEG color image or a PNG monochrome image to the computer using our USB, Wi-Fi, or Bluetooth connectivity. I don't know if you can see down on the bottom of the screen, we have the word start and stop. By touching either the word start or stop, we can define the range of frequencies being swept. And in this example, it's 141 to 148 megahertz. By touching that word points, we can define the number of discrete frequencies between the start and stop frequencies. In this example, it's 201. The higher the number of points, the greater the accuracy and the smoother the graph, but also the slower the sweep time. The touchscreen interface also allows us to include some pull-down menu features. For example, we could add a limit line, in this example -14 decibels. Our color display also allows us to display the trace in different colors, for points above our limit line and for points below the limit line. And as you can see there, everything below the limit line appears white, everything above the limit line appears yellow. We can also add markers and search for minima or maxima. In this screenshot, we have added a marker and searched for the minimum return loss, which in this example is -24.35 decibels. You can see that figure in the top left-hand corner of the screen, and centered on 145.34 megahertz. Again, top left-hand corner of the screen. We can also use these marks to denote the frequencies at which our system complies with our limit line. In fact, our touchscreen allows us to slide them up and down along the graph. So we have here two markers. In this example, we have an antenna and a transmission line with a useful bandwidth of approximately 141.7 to 146.8 megahertz. That's the frequency at which it complies with our limit line of -14 decibels. And again, you can see those two frequencies there in the top left-hand corner of the screen. Just switching back, can you see in the top left-hand corner we have the return loss? Again, this is one of the features of the touch screen. If we touch the word return loss, it brings up a pull-down menu, and we can select here SWR, standing wave ratio. This next image shows us the example of voltage standing wave ratio versus frequency. In fact, it's exactly the same antenna as in the previous example. A transmission line carrying a forward and a reflected wave will have peaks and troughs of voltages where the two waves interact. Voltage standing wave ratio is the ratio of voltage peaks to voltage troughs. In the ideal situation with no reflected signal, there would be no peaks and troughs, so the VSWR would be 1:1. In this real world, the ratio will be higher, with a voltage standing wave ratio of 1.5:1 being equivalent to our previous return loss example of 14 decibels. Again, our touchscreen interface allows us to provide pull-down menus for limit lines and markers. And in this example, the software has automatically translated our previous limit line of 14 decibels return loss into a limit line representing the same voltage standing wave ratio, which is 1.5:1. And you can see that on the left-hand side of the screen. The various figures there represent VSWR. And as we can see here, our minimum VSWR marker shows the same minimum at 145.34 megahertz, time with a voltage standing wave ratio of 1.132:1. And you can see those figures in the top left-hand corner there. As we saw with the return loss trace, we can move the markers to the points at which the trace crosses the limit line in order to show the useful bandwidth of our system. It's the same antenna and the same limit line, so it should be no surprise that the bandwidth is the same, approximately 141.7 to 146.8 megahertz. And again, the figures appear in the top left-hand corner. In those two previous examples, we summed the reflective energy regardless of the phase angle and displayed the results against the frequency in order to show the useful bandwidth of the system, either in terms of voltage standing wave ratio or return loss. In these next few examples, we're using the phase angle to determine the delay for the reflections and using that as our y-axis. A radio frequency signal propagates through a transmission line at a finite speed. The precise speed is a percentage of the speed of an electromagnetic wave in a vacuum, which is approximately 300,000 kilometers per second. That exact percentage is known as the velocity ratio of that cable, and it will vary according to the construction of the cable. Typical values for the velocity ratio of commonly used coaxial cables are in the range 0.6 to 0.8, or 60 to 80%. It therefore follows that if we know the phase angles of the reflections for a number of different frequencies, and if we know the velocity ratio of the cable, we can calculate the distance at which the reflection is taking place, or reflections are taking place. In our example here, we can see that a reflection representing a high voltage standing wave ratio, and you can see the numbers there in the top left-hand corner of the screen, 12.72 to 1. So we have a reflection representing 12.72 to 1 at a distance of 3.55 meters along the cable. This means that if our engineer is faced with a non-functional system of an antenna and transmission line, he will now have a very good idea of where to go looking for the fault. He doesn't need to do a detailed inspection of the whole mast, the cables, the whole system. He's going to know that he's got something major to look at, 3.55 meters along the cable. And looking at that high VSWR, I think he's going to find something fairly obvious, like somebody's hammered a nail through the cable, or we have a broken connection. Having repaired that fault, we can run the test again to ensure that no other faults exist further along the cable. This next image shows an example of one of the pull-down menus. This is the menu in which we can specify the type of cable, from which the tester can derive the velocity ratio and hence the speed of propagation through that cable. You'll notice here it's at the bottom of that menu where it says cable list. You'll notice here that we've selected RG3 from that cable list. It's a commonly used coaxial cable for VHF applications. By selecting that RG213 from the pull down, it automatically populates the velocity ratio and the cable loss fields for us. And you can see there, velocity 0.66 or 66%. In other words, that radio wave or electrical wave is traveling along the cable at 66% of the speed of light, about 200,000 kilometers per second. We can also manually enter these details. If we click on the word velocity, we can type the precise number, and the same for the cable loss characteristics. Or we could edit the database to add an entirely new cable that the system doesn't already know about. The menu also allows us to specify the range of the horizontal distance axis. In this words, 0 to 10 meters. There's obviously no point in having several hundred meters of horizontal range on the x-axis if the cable's only a few meters long. So we can specify those limits, and you'll notice there at the top of the screen, unit is set to m, meters. It gives us the opportunity to specify either metric or imperial units, feet. Use of the pull-down is also a user-friendly mechanism for calibrating the instrument. Can you see there, top right-hand corner of the screen, cal? That's another pull-down. A frequency domain reflectometer should ideally be calibrated every time we change the range of operating frequencies, or when the instrument encounters a significant change in ambient temperature. The calibration procedure involves connecting first a precision open circuit, then a precision short circuit, and finally a precision 50 ohm load to the test port. The pull-down menu for the calibration prompts us through each of these various actions and tells us when each stage is complete. Finally, when the instrument has been calibrated for that range of frequencies, the words correction on, or COR on, appear at the bottom right-hand corner of the display. You can see it there in red on the bottom right-hand corner. Okay, that's VSWR versus distance. But VSWR is a fairly binary thing. It will tell us if something is good or bad, but it doesn't give us the detail we might want to see, and which would be displayed if we had return loss versus distance. And that's what we see in this next example. Just as an aside, I don't know if you can see it there. The previous example showed the distance in meters. If you now look along the x-axis, this time it's in feet. So as I said, the pull down allows us to select either metric or imperial units for our American friends, and they're in feet in this example. Now, no coaxial cable is perfect, and we should expect to see very small reflections along the entire length of the cable. Any compression of the cable, perhaps where it's been clipped down to a surface, or people have used tie wraps, or where it's bent around any tight radius, that will deviate the cable from its nominal 50 ohm impedance. Hence, the reflections will become slightly larger, and you can actually see that that squiggly line varying between about -45 and -85 dB. That is just the background reflections in the coaxial cable. Where it's higher, you could expect to see perhaps kinks in the cable, or it's been turned around a bend, or perhaps it's been crimped by a cable tie. Again, we can use markers to denote any points of interest. And in our example, you have markers 1, 2, and 3. And you can see the list of them there in the top left-hand corner of the screen. Those are in fact barrel connectors, which were used to link a long run of thick, low-loss coaxial cable of the Heliax variety with shorter lengths of a more flexible cable, which are used in the radio room and at the masthead. And finally, the fourth marker is the antenna. As I noted earlier, we can also disconnect the antenna at the far end of the cable. That will be an infinite mismatch, which causes all of the energy arriving at the end of the transmission line to be reflected back to the source. We can use this to compare the forward and reflected power at the source in order to derive the losses of the transmission line at any given frequency. And you can see there we've set the frequency range from 144 megahertz to 1296 megahertz, and it's drawn us a graph of the cable loss for that particular length of cable, which is approximately 20 meters of RG213. Okay, that information allows the installer to compare the losses with the cable manufacturer's specifications for that cable, and to then make an informed decision as to whether the cable is good or bad. A common fault in coaxial cable is moisture ingress, and this can cause losses to rise without necessarily affecting the characteristic impedance of the cable. This can actually cause the VSWR in the system to be reduced, and so the fault could easily go unnoticed with a simpler test procedure, such as just testing the system with a transmitter and a VSWR meter. In our example here, we can see that our 20 meter length of installed cable has a loss of 1.8 dB at 400 megahertz, and moving further down that graph, you can see it's about 3 dB, 3 decibels at 1000 megahertz. If we compare figures with the manufacturer's specifications, which are in this case they're for 100 feet of cable or 30 meters, we can see that our measured figures are approximately 2/3 of the figures from that table, because it's a 20 meter cable, of course. So we can conclude that that cable is performing as it should. Our Android-based platform with USB connectivity also allows us to use the device for other purposes as well. For example, we can use the device as a display for an external RF power sensor, such as the RF2020 power sensor pictured here. The display is just a simple app which reads and displays data from the attached sensor. The real work is being done within that sensor. As a point of interest, the same app will run on any Android phone supporting the OTG or on-the-go connectivity feature, allowing it to act as a display for any of Bird's current range of USB RF power sensors. And we have sensors covering the range of frequencies 2 megahertz to 6 gigahertz. So all of the frequencies used for land mobile radio, cellular and Wi-Fi. Our USB, Bluetooth and Wi-Fi connectivity also allows us to export data or screenshots to nearby devices. For example, we can export either a JPEG, color, or a PNG monochrome screenshot of a return loss sweep to a PC and use that in our site handover report. What you've been looking at previously were JALA images. This is what the PNG, the monochrome image, would look like. And in fact, this one is the return loss of a vehicle-mounted Tetra antenna on a police car. You can see there it's performing very well. We've got a return loss of over 30 dB at 380 something megahertz, which is more or less where it should be for the uplink on Tetra. That same connectivity also allows us to share S11 parameters as a CSV or Excel file with other devices. As you can see here, we've got the frequency in the left-hand column, 130, 130.1, 130.2 megahertz, and so on. And then we have the real and the imaginary parts of the impedance in the middle and right-hand columns. You'll also see at the top some information such as the date and time of the sweep, the location. If we're outdoors, of course, it would be able to pick up the GPS and insert that. This was obviously taken indoors where there was no GPS coverage, so it's just showing the default 00 for latitude and longitude. And finally, whoever did this didn't calibrate the device first because it's telling us calibration is off. Okay, all those previous slides showed how a relatively old technology can be revitalized with the millennials technology, creating a powerful tool for testing antennas and transmission lines. We're going to look at an even older piece of technology now, the frequency spectrum analyzer. We can see what can be done by adding GPS, an integral compass, and an online mapping technology, again, using an Android platform. Frequency swept spectrum analyzers, there's a tongue twister, isn't it? Frequency swept spectrum analyzers have been with us in one form or another for over 50 years, and they allow us to view the local RF environment in terms of frequency versus amplitude. By building such a device into our Android platform and integrating it with GPS, an internal compass and Wi-Fi to give us access to online maps, we can build a simple yet very effective tool for hunting sources of radio interference. So let's take a closer look at such a device. Like any other spectrum analyzer, we have control of the frequency span. You can see it in the bottom of the screen, and of the video and resolution bandwidths, and they're over at the top of the screen on one of the menu bars. This means that having identified an interfering or an unlawful radio transmission, we can then zoom in and focus our analyzer on that signal alone. So in the left-hand picture, you can see the spectrum between 390 and 395 megahertz, and that's widely used throughout Europe for the emergency services Tetra networks, and that's the downlink frequency range. You can see a few peaks there, so we're in range of a few different base stations. But we have a suspect signal that shouldn't be there. An interfering signal's been noticed, and we place a marker on it. And you can see that in the middle picture. And then we can narrow the swept spectrum to zoom in on just that one signal. And you can see there at the bottom of the screen, we've zoomed in on that frequency range. We can also close down the resolution and video bandwidths in order that the instrument only sees that one signal. So in this case, we've set it to 30 kilohertz, which is just slightly larger than the channel spacing for Tetra, which is 25 kilohertz. Back to the Android features, the instrument has an app called AOA Locate, where AOA stands for Angle of Arrival. This app ties together the spectrum analyzer functionality, our internal GPS receiver, an internal compass, and I'll come on to the function of the compass later, and an external source of online maps, which are accessed via the instrument's Wi-Fi capabilities. Now, most likely we'll be out of range of any fixed Wi-Fi services. This is something you use in the field. So we would probably use the hotspot feature of a mobile phone to give the instrument Wi-Fi access to the online maps. Or Bluetooth, of course. We have Bluetooth, and a number of phones can share their connectivity through Bluetooth. Based on the position data from the GPS receiver, you have the lat and long down on the bottom screen, and the data from the online maps, the instrument can display a map of where we are. You'll notice that the frequency and the bandwidth parameters of the spectrum analyzer are displayed at the top of the screen, together with the bar graph for the signal strength of the top left. You can see that bar graph showing red, and I think it's about -70 that's showing. A bit difficult to see on my screen, it's minimized. Together with our current latitude and longitude at the bottom left. Okay, remember what I said earlier about that compass? This is why we need it. Yeah, that is me in the left-hand picture. I've got longer hair now because I've been locked up for 9 months. As you can see, I'm holding the device in alignment with the Yagi antenna. That's important because we want to be able to use whatever antenna is most appropriate for that particular application. And so we don't rely on the antenna having a built-in compass. Now I rotate the antenna and the instruments a few times. This does look a bit peculiar when you do it, as you can imagine. So I rotate the antenna instrument a few times, and you can see the middle screen builds up a number of samples until it's able to determine the direct strongest signal, at which points it paints a red line on the screen, and we can see that there. Just before I move on to the next page, there's a school of thought that suggests the compass should be integrated with the antenna. And in fact, there is a product on the market for this application that works in precisely that way. We felt there are some issues with that approach, which is why we didn't adopt that solution. It makes the antenna system proprietary because the data and power connections to the electronics within the antenna and in the compass functionality will be specific to the spectrum analyzer. Secondly, since every customer's frequency range of interest might be different, the antenna would have to be a trade-off of gain versus frequency versus size and weight. So it'd probably be some kind of log periodic design. So by using the compass functionality within our instrument rather than within the antenna, we only need the connection to be just for the antenna, so a single 50 ohm coaxial cable connection. Then the customer can choose whatever antenna meets his own requirement for frequency, gain, size and weight. So as an example, the antenna pictured there, you can just about see it. It's a 3-element Yagi for UHF frequencies, and it was in fact intended for amateur radio and PMR 446 users. Very cheap. I purchased that one on Amazon for €60, and it does the job. When I press the save button, having got that red vector, the app will store my position together with the vector of the strongest signal and put those on the map. In this case, the strongest vector is at 103 degrees, in other words, just slightly south of east, and you can see there on the screen the long black line is the vector of strongest signal. You can also see there the strength of the signal, our current latitude and longitude, and the date and the time. This is where I jump in the car and drive to another location to take a cross bearing. When I repeat the process, the previous vector is saved in a different color. And you can see there our previous vector is now in red and our new vector is in black. Hopefully, doesn't always work, but hopefully they're going to cross at some point. And that gives me a pretty good idea of where the problem signal's originating from. It also gives me a very good idea of where to take a third bearing from. So I'd probably position myself somewhere to the north or somewhere to the south of where those two lines cross. Okay, look, I cheated a bit on this slide. In reality, the crossing point of those three bearings are unlikely to be this precise. You'd more likely get a triangular shape, and that would give us some idea of where to drive closer to, and then we will take further bearings with the attenuator switched in and or with the preamplifier switched off. So just to recap, we've seen how the technology of the millennial can be used to enhance the user-friendliness of the test equipment used by the installer or maintainer of radio transmission systems. On this final slide, you can see the URL for the Bird website, at which you can find a link to our recent Discover RF with Bird free seminars, which include subjects such as RF fundamentals, cable and antenna measurement basics, distance to fault measurements, spectrum analyzer basics, triangulation, a more detailed overview of what we've just done with angle of arrival, and a presentation on wireless coverage with DAS systems. Finally, Bird has a YouTube channel which includes video clips explaining the technology and usage of our products. Just search for Bird RF on YouTube and I'm sure you'll find us. I hope that's been of interest to you. Please feel free to contact either me or my colleagues at Heynen in the Netherlands or Belgium should you require any further information. Handing it back over to Mark now.
Thank you very much, Mike Gettigood from Bird Technologies for this presentation. The presentation, what Mike also mentioned, is on behalf of Heynen. The contact details will also be shared of Mike and Heynen at the public chat. We now have time for questions. I don't see questions yet, so please ask. We have some time left, so please ask your questions in the public chat, and Mike can answer them straight away. Let's wait around 20 seconds if questions are coming in. Already maybe good for the followers. We have some also more webinars these days, 4 more webinars. The next one is at 10:30. That's a presentation from Dirk Faber from High-Tech RF Solutions. It's live from the FHI studio. And the subject of his presentation is Insight by Characterizing Uncertainty in S-parameter measurements. So that's the next presentation. After that, we have a presentation also from Patrick Dijkstra from Raditech. And after lunch, we have a presentation from Suzanne van Dijk from Sorama. And also the last but not least presentation from Michel Brentjens from Astron. I don't see any questions yet, Mike, so I think...
Okay, well, is that a good sign, or does it mean that nobody was listening?
I think it's a good sign that there was a clear presentation. And if there are questions, they can also contact you or Heynen afterwards. We will also share a presentation the day, so tomorrow, with all the followers, also all the people registered for the webinar. And also we put it on demand on the website, so more questions will definitely come. Thank you again, Mike, for this interesting presentation. Thank you also, Dennis Delaroy from Heynen, for being the moderator today. And we hope to see you at one of the next webinars. And have a good day. And thank you, Mike. Bye-bye.